Welcome to Breadboarding. In the previous video we managed to get the 7-segment LED display and the keypad based on the Adafruit NeoKey keypad plugged in and working, and we managed to get some test software running in the EEPROM that would at least allow us to test the LED display and the codes returned from the keypad. So this is video 5 in the Breadboard PC 8088 version 2. And in this video we're going to be updating the 8086 version of the Nanocomp monitor to work with the new display and keypad. This is part of the high-level plan, and you'll see that in this video the number 11 refers to the original Breadboard PC playlist where we would have covered this in more detail. I went into more detail about the conversion of the 6809 code into 8088. And this is the plan we're following, which is a little bit compressed compared to the previous series, where we're going to get this initial Nanocomp working, first of all with the 7-segment display, keypad and monitor, and the serial port able to save and load programs from the serial port. And then we're going to be building out the basic floppy disk PC able to boot off floppy disk, and then we'll be extending that to cover the hard disk, enhancing the CGA video controller to do graphics modes, getting a PS2 mouse working, and then eventually we'll be running Windows 1, 2 and 3 like we did in Series 1. So this is the block diagram we've been working off. So we've completed all of this so far. In the previous video we wired in the 7-segment display port and keypad port and all of the supporting logic here. And what we're going to need to do is to add the reset and abort buttons, so we didn't do that in the previous video. So this allows us to initiate a reset if something hangs for some reason, and the abort key is actually used to jump into the monitor, display registers, so that we can actually look at debugging running code. So why do we need a monitor program? So the Apple I included a very simple monitor called Wasmon, which was coded in 248 bytes, and Ben Eater has done a good video on this, and he goes into the detail of this and I think recreates Wasmon on his own 6502 based microcomputer. So Wasmon would allow you to inspect memory, enter values and do basic amount of debugging. Then in the early days, Tim Patterson of Seattle Computer Products, who was one of the first developer for 86DOS, which then became MS-DOS, apparently in the early stages of developing 86DOS, he used a version of debug in ROM, and this version eventually became debug.exe in MS-DOS. The documentation on debug was not really great in the beginning, and there's a lot you could do with it. However, it wasn't the easiest to use of programs, but it is actually quite powerful. And then in the early 80s, a lot of the early computers before the PC had a basic ROM, generally Microsoft Basic, so the Commodore PET, BBC Micro, Spectrum, Dragon 32, TRS-80 all had built-in basic and had similar features. For example, the Dragon 32 included some documentation that said for users of machine code, for example, you could use the machine language code can be put in memory using an editor or assembler or a basic program using poke. You can use peek and poke commands, and then the def user and user commands would allow you to jump to machine code. So even using the built-in basic, you could do some simple coding using machine code. Although I used the Mace macro assembler, was a plug-in cartridge, in fact, for the Dragon 32 that I have fond memories of. So we need a monitor basically to provide something for when the computer powers on, gives you some sort of functionality. And what we'll be doing is building out the monitor first of all, so that we then can start to get the BIOS working. Once we've got a BIOS, that will allow us to boot an operating system like MS-DOS. So the Nanocomp monitor is a very simple operating system. I don't think you'd really be stretching a bit to call it an operating system, but it was from the original 6809 Nanocomp project from back in 1981, and I had a copy of the ROM actually in EEPROM from back in 1981. What the monitor will do is initialize a stack, reset interrupt vectors, and in fact in the 8088 we need it to initialize the segment registers, allow you to inspect and change memory, execute programs given a particular starting address, display register values after a breakpoint. So on the 6809, that was the software interrupt 3F, and on the PC and the 808886, then that is interrupt 3, which is CC in hexadecimal. Now, the original Nanocomp supported loading and saving memory to tape. That was replaced with saving and loading files over the serial port using the Motorola S-Record format, SREC, which is just a simple text format to allow transferring binary data. The original monitor was written in Motorola 6800 assembly code. It was then updated to work with 6809 in the July version of the Nanocomp in 1981. In the Nanocomp 6809 video 12, I reverse engineered and disassembled the original monitor ROM that I had with help from Mike Spivey's Nanocomp 6802 ROM disassembly at this location. I'll include the URLs in the description below. So Mike had actually done a disassembly of the original 6802 ROM, which helped enormously in working out the differences with the 6809 version. And then in the 8088 Breadboard PC version 1 series, which there'll be a link up the top right hand corner of the screen here to this video, then in video 11 we converted the monitor from the 6809 assembly language to 8088. So I'm not going to go through the changes that we did there, but we need this 8088 monitor to build and test the hardware to run and debug the XT BIOS that we need to run up MS-DOS. And this is the display that we've got from the Breadboard PC Series 1, the Nanocomp 8088 version 5 monitor. This is the version of the software that we're going to be using to update with the changes that we tested out in the previous video. So just review what the monitor does. So we've got the keypad here. So we've got the load, save, continue, go, code segment, extra segment, memory, register, and increment keys here, as well as hexadecimal keypad here going from 0 up to F. So the M key allows us to inspect and change memory, and we just keep on typing keys to change the byte values, and then when we press increment, then it will save those changes. It will also read back the memory. So if we're trying to save, for example, the memory to ROM, then in fact when it reads back the value, it won't be correct, and so it'll actually just jump back to the monitor prompt. Go allows us to execute a program at a given address. Now, because of the 1 megabyte segmented memory model that the 8088 and 8086 had, then in fact what we need to do first of all is set the code segment first for the top sort of 4 address bits that we need to specify, and then the go command allows us to put the lower 4 hexadecimal address values in. The save and load we're not covering here because we haven't installed the serial port yet, so we'll cover that in another video. Continue allows us to continue from an interrupt free, so if there's a software interrupt, the CC hexadecimal code, so we can use that for debugging things, and when we hit that int 3, it will then display the register values, and continue will allow us to continue back where we jump from and carry on from the next instruction. Register does a register display and will also be automatically called on an interrupt. Increment is used by the memory command and by the register command. So memory takes us from one memory location to the next. So if we don't type any changes, then it just sort of goes on to the next location. And in the register display, increment just takes us to the next register. And then these are 2 extra commands that I added as part of the 8088 conversion. So ES allows us to set the extra segment, and that is used for the memory inspect and change and for the save and load. That would allow us to load, for example, programs into, say, the upper area of memory, so perhaps the segment starting with 7000, for example. And then the code segment then allows us to set the code segment register as well for the execution of that. Now, what we also need to do, in the original keypad, the reset and the abort key were actually on the keypad here, but because those need to be wired into hardware lines rather than this matrix, I've actually got some separate keys to put in there. So as part of this video, we're going to wire up the reset and the abort button, which actually does the non-maskable interrupt. So let's take a look at the changes that I've needed to make. So I've got version 6 of the monitor here, which is a new version compared to version 5, which is the version that we saw from the LED display previously. And a number of changes I've gone through here. I'm only going to cover them in summary because we kind of did most of the changes in the previous video when we were doing the updates necessary to the test program to handle the new ports and the NeoKey keypad. So NeoKey keypad, we're now using the ports at 400 and 401. We've got the new key code, so I've updated the key codes. And we've also got the 2 new keys for the code segment and extra segment. We're going to be adding the serial port in the next video, so there's just the address that we'll be using for the serial port coming up. Now you'll see that the control port A and control port B are no longer needed because we're not using a peripheral interface adapter, PIA, or parallel port. We're just using sort of hardwired LS logic ports. And I've updated the display to show version 6, so we know that we're running the later version. We're now dealing with rows 0 to 4 or row 1 to 5 if it's 1 index rather than 0 index. So we just need to increase some of those values. The last digit will now be 0D rather than 0C when we've gone beyond the last digit. Now we're also rather than using 7F, I'm now using FF to turn all segments off because we've enabled the decimal point as well. So if we want to, we can now use a decimal point. Then we've got, again, the new code for the new keypad. Then the get key probably has a few more changes in. Again, all of the control port initialization is now removed. And there's just a few changes to some of the comments. So the version 6 monitor has now, those changes have been done. And I was thinking, should I just do the monitor on its own or should I just leave it still incorporated with the BIOS? But I decided it's probably easier since we're going to be doing the BIOS soon. What I've done is, here is the BIOS that we used in the previous version of the Breadboard PC. And this actually referenced and included the monitor within it. And all I've done is I've changed this from version 5 to version 6. It's probably easier to do this and then we'll come and look at the BIOS at a later point. But this at least means I don't have to change any other code here. So what we're going to do, in fact, is in assembling the monitor, what we're actually going to do is to follow the build instructions for the BIOS where the monitor is actually incorporated. So we're just going to make that. That's all finished without any errors. So what this means is when we're programming the EEPROM, we just need to make sure that we allow a space at the bottom of the EEPROM for the IDE BIOS when we add that. I'm just going to start up XG Pro. Just going to take the EEPROM out of the 0 insertion 4 socket, make sure it's the right way around at the bottom there. So it's in the programmer. So just going to read it first of all, make sure it's in the right way. And you can see here, this is the code, the test code that we used previously. There's only a little bit of that at the beginning. It has the reset code. Now we're going to load the BIOS file, which includes our monitor. So by default, this starts in the monitor, and then when we press B, it then actually starts the BIOS. So we're all set up then for when we start to add the PC compatible parts of this to the computer. Now the only thing we need to do is we need to make sure we load this from 4K into the 32K EEPROM. So this allows us to have the first 4K being the XD IDE BIOS. So when we load this, you'll see that when we go from here down to 100, you'll see here the first 4K is all Fs, and then we have the BIOS starts there. Then some of the way down there will be the monitor, and then at the end you can see here we have the reset code that actually jumps to F000C00. So the monitor actually starts at C000. Okay, so we're just going to program that. put the EEPROM back into the socket. And we'll try powering up. So what we'd expect is it should come up with NC8088-6 version 6. That's good. So it's come up with Nanocomp 8088 version 6. And if we now press key here, we now got the Nanocomp prompt. And if, for example, we wanted to look at 000 memory, we can see that there's the memory there. The load and save aren't going to do anything at the moment. And if we hit R, we'll get the registers. So that is the flags there. Code segment, instruction pointer, stack pointer, the AX, CX, DX, BX, the base pointer, the source index, the destination index. So those are the registers that we need to worry about. Just try setting some memory. So we've set the code segment to 7000, the extra segment to 7000. So this is the top bit of memory just below 512K. If we go to 000, so I've already put 00, 01, 02, 03 in there. If we go back and try and change that to FF, FF, FE, FD, FC. We go back and have a look. FF, FE, FD, FC. So that appears to be working. If we tried to do this in the ROM area, for example, so if I change the extra segment to F000, for example, and then we go to FFF0, can see this is EA00C000F0, so that's the reset code. If I try to change this, so change that to FF, you'll see it doesn't save it properly because it's read-only. It goes back to the monitor. So if we try and make a change and the memory can't save it, then in fact it goes back to the monitor. Now at the moment, my reset button is this light, is this wire here. So if I ground this momentarily, you'll see it will go red to show that it's in reset. And at the moment, you can also see that the display here is actually latched on. Now, I did do some changes to avoid this, but I think I didn't quite account for one thing that we're going to need to look at. So when we're in reset, we're actually getting one segment sort of burning quite brightly there. So if I take it out of reset, it goes back to the Nanocomp. So that's something we need to look at to see if we can fix that. We really would want all the LED display is off during reset. Now, these are the buttons I was going to use for reset. Now, originally I'd intended to try and put these over here, but when I tried it out a little earlier, what I was finding is by the time all the wires came all over here, there was enough interference on the reset button line that in fact it wouldn't actually go into reset. So what I'm going to do instead is we're just going to put these down the bottom here. And I'm going to wire in the, turned off at the moment, I'm going to wire in the ground line first of all, very close to the chip here. We'll wire in the 5 volts as well. And then this is going to wire in the non-maskable interrupt actually to 5 volts. So we're just going to change this now that the push button reset is now going to go to here. We'll leave the interrupt the moment. All I want to do first of all is just to make sure to see can we now reset this rather than using our yellow wire here to do it. Can we now actually do reset? So if we turn it on and if we go into the monitor here, if I press the reset button, we should see the red light come on when it's held down. We might see a segment illuminate here we need to fix, and then when I release it, then it should after about half a second go to green light, and then we should see the Nanocomp display message. Okay, so that is definitely resetting, and we see the segment there illuminated. Release it. Right, that's working okay. Now I'm just going to turn it off again, and this is wired to, this button here is wired to 5 volts, and we're going to plug this into the non-maskable interrupt. There we go. So this is now plugged into the non-maskable interrupt. So what this should do is actually take us back to the monitor. So if I go into here, doing something, and if I press this, yes, it takes it back to the monitor. And if we want to, we can also then press the R to display the registers, what we're at. That seems to be working. So I've got the reset button and the abort button, which does the non-maskable interrupt. That will always allow us to interrupt the BIOS or something like that if we need to do any debugging. And we can also see that the green go light means that the processor is running. The red light means either there's a power problem or we're in reset. So the only thing we need to fix now is this sort of segment here, which seems to be illuminating when it's in reset, which I did include some configuration in the PLDs to prevent that, but we need to have a look and see why that is occurring. So let's take a look at the PLD configuration and the schematic. If we look at the schematic, the intention was that when there was a reset, that we would actually set all of the SP0 to SP3 lines to 1. So these would all be 1s, and so this would mean that it would be out of range. So either when we looked at the datasheet, we saw that anything above 9 would end up with none of these outputs selected. I had a look at the PLD configuration, and although I had set these to be set to 1 when there was a reset, the trouble is that the preset is actually synchronous with the load B. So unless we can actually get load B to clock this, then in fact the preset won't actually work. So if we actually go to the PLD here, so we can see here that the load B is the clock that's coming in from the control PLD. And we can see here that we've actually set the synchronous preset for this to be the reset. However, this will only take into account if load B goes from low to high. Now, I had a look at the other PLD to see how easily that would be to do, and it isn't actually particularly straightforward. And so what I was thinking is, all we really need to do is SP3 is not actually used for anything other than this reset condition. So what I might be able to do is to change the rules here, and actually, rather than using this table to do the mapping, what I might do is comment this out and put in the rules that this generates specifically, and I'll just include that the SP3 will just be set to reset. So when reset is active, then SP3 will be set to high, and it will mean that none of the displayed segments will actually be output. So if we have a look at the doc file that's generated, we can see that in fact that the values for the SP0 through to SP2 are actually included here, so we can actually just copy those into here, and the SP3 as well, and all we need to include in here is an OR that says OR reset. Okay, so I've done the changes, so this is version 3 now, and all I've done is down the bottom here, I've now disabled the presets, because without the clock on the load B, then under reset that won't occur. So now what we're going to be doing is setting SP3 to 1 during reset, and I've commented out the table mapping here, but I have been able to use the generated rules from the documentation file. So I've just put in the rules there for SP0, 1, 2 and 3, and then I've just added 3 that if reset is enabled, then in fact this will be 1. This should actually prevent the digits from occurring. We just need to compile this and program it. So just turn the project off because it will crash if the project view is enabled. So I'll just compile that. That's compiled successfully. So now I'll just program the PLD and put it in and see whether or not that works. Okay, so that's all plugged in, programmed. Let's try it out, see if it works. Okay, so that looks okay, so that's working so far. So now let's press the reset button and see if that results in a blank display or we still have any segments left. That didn't do any good. So back to the drawing board, let's have another think. So in fact, what the problem was in the changes I made here, I'd forgotten that in fact the SP3D, this was still latched, and so the reset would only take account if there was a clock, the load B clock signal, so it wasn't any better than what we had before with preset. But what I did notice is we've got a spare output pin here. So what I've done now is I've changed this pin to be the latched SP3 for reset purposes. And what I'm now doing is just combining that output there with reset for this one here. So when reset occurs, then this will immediately change. It's not dependent on a clock. So let's just look at the pins here. So we've got our pin 14 SP3 reset, and what's going to happen now is I've just changed the SP3.D to SP3 reset.D. So this is the one that's going to get latched on the clock, but then the SP3 output is in a combination of this one here and reset. So that hopefully should sort it out. So all I'm going to do is to recompile that, program it, and then we'll fit it in the circuit and see if that's fixed the problem. Okay, so the updated PLD's been fitted in here. So we're just going to power this on, make sure we still get the display, and it's going back to the monitor prompt. If I press reset now, what we'd expect to see is the display to go completely blank, which it has. We get it back, and if I press this again, yeah, blank, that would appear to be working. So that's good. And then the abort still works. So if we're in something like this, press abort. Great. So those two things are working. I might try and tidy this up at some point in time, but I didn't really have enough space to put this in the board up here at the time. I think probably keeping it separate for the moment will be fine. Those changes have been done. We've wired in the reset and abort. We've got our monitor working. Now the only thing we haven't been able to test yet is the save and load from the serial port. And so what we'll be doing in the next video is we'll be adding a modern serial port. So this is in fact a 165550 UART. So this is one of the faster ones. And in fact, this one happens to be a surface mount device, which I have got a video of soldering a surface mount device onto a DIP connector that we'll look at in the next video. And then we'll also just test that we can download S-record file format binary files and load and send those as well. So if you don't want to miss out on future videos, then please hit subscribe. And if you can hit like, it just helps to make the videos available to more people. Thanks for watching.